Okay, so the pressure exerted by the vapor, it is directly proportional to mole fraction of the component in the liquid phase. If we equate this, we should introduce a constant called Henry's law constant into mole fraction of the component in the liquid. Okay, so as mole fraction increases, solubility increases. So here solubility, right, is nothing but mole fraction of the component in the liquid, right? So solubility increases, right, as mole fraction increases. Simple. Solubility increases as mole fraction. If mole fraction increases, solubility will increase. Okay, right? Or if I rearrange this, I can write Henry's law constant KH as P by X. Okay, so if solubility increases, that is, if mole fraction increases, KH value will decrease. I have told you in the last class, right? Lower the value of KH, higher is the solubility of the gas in the liquid phase, right? So this is what we call as Henry's law. In the last class we discussed about this. Okay, now we'll discuss some of the applications of this Henry's law. Okay, right, we have a few applications. We are going to see two applications here. Number one, see, in the manufacturing of soft drinks, right, and soda water, right, in the manufacturing of soft drinks and soda, usually the container is sealed, okay, with under high pressure, right? So suppose if this is the shape of the bottle, just assume like this. Okay, the container is sealed. The container is sealed with high pressure. Okay, you have liquid here. This is the liquid, and here we have what is it called? Carbon dioxide gas. Right, the container is filled with CO2 gas above the liquid, and CO2 gas is filled with under high pressure. Why under high pressure? The reason is to make CO2 more dissolve in the liquid phase. Okay, under high pressure, solubility of CO2, right, increases. Therefore, you will get more dissolved gas, right, in the liquid phase. As you all know, CO2, right, dissolved CO2 in water will give a compound called carbonic acid. So soft drinks, right, they contain acidic compound called carbonic acid. So if people have acidity, right, if people have problem with acidity, they are not supposed to drink soft drinks. The reason is, okay, it has under high pressure, they should not consume as such actually. Okay, just by opening the soft drink, and if they consume as such, okay, then they'll suffer with the acidity problem. Okay, so so it is better to avoid soft drinks, right? Or you can have soft drinks occasionally, or rarely you can take, right? Not regularly, right? Okay, so that's the point you should keep in mind. Yeah. So why CO2 is filled under high pressure or sealed under high pressure in soda and soft drink? The reason is to increase the solubility of CO2 in water. Okay. Yeah. Then second important application is about this scuba divers. Okay, so you might have seen this. The people will go deep inside water, okay, specifically sea water or river something, okay, and they'll do some research. Okay, while going down in the underwater, okay, they'll go below 500 meters or 1 kilometer, like that. When they go below, right, they'll carry the tank. Okay, you might have seen that. The tank actually consists of oxygen. Okay, not pure oxygen, because oxygen density is high, right? Just assume like this. So we have some person, right? The person carrying some gas tank. Okay, that gas tank consists of oxygen. But the problem is when they go deep inside water. So if this is the water level, when they go deep inside water, what will happen? Since oxygen density is very high, the oxygen gas may not enter into their nose. Okay, so they'll get breathing problem. So what they'll do, they usually mix nitrogen gas. So in the scuba divers, right, the gas tank that they carry, they consist of the tank consists of mixture of oxygen gas and nitrogen gas. Okay, so nitrogen gas density is less. So when nitrogen gas comes out, it will carry the oxygen, right, along with it, and so that the people can inhale oxygen freely. But there is another problem here. When the scuba divers reaches, right, when the scuba divers reaches the surface of water, what will happen? The dissolved nitrogen gas will starts to come out. Students, observe carefully. The scuba divers, right, see underwater. So assume that this is water level, right. When the scuba divers is below, right, they'll carry tank, I told you, right. From the tank they'll get oxygen gas continuously, right. But density of oxygen is high, right. Therefore the oxygen may not come out freely. So to bring the oxygen freely to the nose, what they'll do, they'll take a mixture of oxygen and nitrogen. So when nitrogen density is low compared to oxygen, so when nitrogen comes out, it will carry the oxygen along with it. Therefore people won't get any suffocation. Okay, but the problem is when the person reaches the surface, right, when the person reaches the surface, the dissolved nitrogen starts to come out. Okay, so it starts to bubble out from the blood. Okay, the nitrogen gas get dissolved in blood, right. This dissolved nitrogen starts to bubble out. When it bubble out, what will happen? It creates a medical condition called bends. It will create bends. Okay. Listen, in the right, there are a lot of blood capillaries are there, right. In the blood capillaries, right, the nitrogen bubbles may struck, and it will obstruct the flow of blood. Okay, that is what we call as bend. Whenever bends created in blood capillary, okay, the people will get lot of pain, and it is very dangerous also. Okay, they have to remove the bend immediately, so they will do some operation procedure and all. Okay, so to avoid this bends problem, what people did was, okay, they took this mixture actually, right. Instead of taking only oxygen and nitrogen, if you take oxygen and nitrogen, okay, nitrogen content will be high. When nitrogen content is high, you will get a problem called bend. To avoid this bends, right, what people did was they took another mixture. Okay, that mixture consists of air, okay, right, filled with air, and that air is diluted with helium, helium gas, nitrogen gas, okay, and oxygen gas. Right, they have taken air, that air is diluted, so that air consists of 11.7 percentage of helium, 56.2 percentage of nitrogen, and 32.1 percentage of oxygen. So now the air is diluted with the addition of helium gas. What this helium gas will do, that helium gas will never allow the formation of bends. Okay, it will never allow the formation of bend. Therefore, people never get any problem due to the dissolved nitrogen in the blood capillaries. Dissolved nitrogen in the blood capillary create a medical condition called bend. The bend, whenever bend formation occurs, okay, it will create a lot of problem. Okay, so to avoid that, people mix helium also along with the mixture. Therefore, you will get a dilute air. That dilute air is good. It will never create any problem like bends. Okay, so this is another important application of the Henry's law, right? Because when you go down under, if you go deep underwater, the pressure will be high. So you have a lot of water, and because of the water, right, the pressure in the tank will increase. Due to high pressure, more nitrogen gas get dissolved in the blood capillaries. Okay, so when they reaches the surface, right, these dissolved nitrogens will supposed to come out. When they come out, okay, it will create a problem called bend. So to avoid this, people, what people are doing is they mix some amount of helium gas along with the mixture. Whenever you mix helium gas, right, so the problem of bend can be avoided. Right, you will never get any bend problem. Okay, so this is another important point. You just keep in mind. Then another application is it clear, student? Any doubt in this?
No, sir. No doubt.
Okay, right. Then a third important point is that whenever people go to high altitudes, right, so if they go mountain, right, okay, you know, we'll suppose assume this is a mountain, right. Listen, on earth, right, on earth, the high oxygen pressure or the air pressure will be close to 1 atmosphere. So people living in the earth's surface, okay, they will never get any problem of suffocation. They'll give sufficient amount of oxygen. So the oxygen concentration in blood, right, O2 in blood, O2 concentration, so I'll put the square bracket like this, O2 concentration in blood, right, is sufficient, right, on the earth surface, right. Why? Because the pressure is on earth surface, pressure is 1 atmosphere, air pressure is 1 atmosphere, so people will get sufficient oxygen. But what happens when they reaches the high altitudes, like say if they climb mountain, right, and reaches the top, suppose if people reaches top, right, you know very well, as you go above the sea level or above the earth surface, pressure starts to decrease. So air pressure at the high altitude, okay, may not be 1 atmosphere. It will be say it will be around, say, 0.6 atmosphere, like that. I'm just, okay, roughly I'm giving. It depends upon the height. It depends upon the height of this altitude. Okay. Now, when the pressure goes down, what will happen? You know very well. According to Henry's law, if you have high pressure, more gas will dissolve. Okay. So on Earth's surface, pressure is 1 atmosphere. Students, turn on your camera, everyone. Students, turn on your camera. Right. So on Earth's surface, pressure is high, so sufficient amount of oxygen gas dissolve in blood. But when the people reaches the top of mountain, okay, or when you go to high altitude, what will happen? Pressure decreases. So pressure at the top of mountain will be usually less. Okay, it depends upon the height. Suppose if it is 0.6 or 0.7, I'm just giving this value roughly. Right? What will happen? Pressure decreases. Therefore, dissolution of oxygen in blood also decreases. Right? So oxygen concentration in blood decreases, right, when the person reaches high altitude. Decreases at high altitudes. Okay, whenever oxygen concentration in blood decreases, okay, people will get problem, right? So this mountain climbers, right, sometime they will get this low oxygen concentration in blood, and this condition is what we call as Anaxia. Okay. So when you go to high altitude, oxygen pressure decreases. Because of low pressure, oxygen concentration, because less amount of oxygen will dissolve in blood. So oxygen concentration decreases. Therefore, whenever oxygen concentration decreases, people will become weak. Okay, they are unable to think. You know very well. Everyone requires sufficient amount of oxygen in blood. Whenever oxygen concentration decreases, okay, if it goes slightly down, people will yawn. Yawning will occur. If the decrease is more, then they cannot even think. Right? They'll get a lot of problem. Okay, and that condition is what we call as Anaxia. Right? Anaxia is nothing but low concentration of oxygen in blood. That's all. Okay, so these are all some of the important applications of or important information that we gain from Henry's law. Right? Is this clear, student? Any doubt? Is this clear?
Yes, sir.
Yeah. So what is Anaxia? What is Anaxia? What is Anaxia?
At higher altitudes,
Yeah.
oxygen in blood decreases.
Yeah, very good.
It causes anoxia.
Yes, ma'am, good. So it is actually Anaxia is it's a symptom actually, right? It is a condition. Anaxia is a condition in which people will become weak and they are unable to think due to low concentration of oxygen in their blood. Okay, yeah. So that's why whenever you go to mountains, right, elder people, right, they'll get this suffocation problem, right? It is quite natural because pressure at the top will be usually low. Okay, yeah. Then, so this is some of the important points that we should know. These are some applications of Henry's law. Okay, now, so with this we have completed the part called solubility. Now let me move over to the next important part called vapor pressure. Right here. Vapor pressure. Yeah. Students, observe this carefully. Vapor pressure. What is meant by vapor pressure? Suppose I'll take a pure liquid in a closed container. Students, observe this carefully. So it's a closed container in which I have a pure liquid. Okay, it's not a mixture. say it is pure water or pure ethanol, right? So I am taking pure liquid, some pure liquid. Say for example it is liquid A, some liquid. Now at given temperature T or at constant temperature T, the molecules present on the surface of the liquid, okay, will escape from the surface. It will escape from the surface and reaches the empty space that is available here. This process is what we call as evaporation. Right? This process is called evaporation. So evaporation means molecules move from liquid to vapor. Molecules move from liquid to vapor is what we call it as evaporation, and evaporation occurs at temperature less than boiling point. You know very well. It is not boiling point, right? Assume that it is below boiling point, right? Below boiling point, you take some temperature below boiling point, and the temperature should be constant. At constant temperature, what will happen? The molecules present on the surface, they will escape from the surface and they will occupy the empty space, and this process is what we call as evaporation. Then after some time, what will happen? The molecules which are present in the vapor phase, they starts to approach the liquid surface, okay, and get condensed. Okay, the molecule present on the vapor phase, they approach the liquid surface and get condensed. This process is what we call as condensation. This process is called condensation. So what is condensation? In condensation, molecules move from vapor phase to liquid phase. Right? Then what will happen after some time? Okay, the two process, that is rate of evaporation and rate of condensation, become equal. Okay, and that stage is what we call as equilibrium stage. Right? So when the rate of evaporation is equal to rate of condensation. Okay, if the speed with which evaporation takes place, if it is equal to the speed with which condensation occurs, right, rate of evaporation, if it is equal to rate of condensation, we call that stage as equilibrium stage. So equilibrium is attained. Okay, you'll get an equilibrium. At equilibrium, students observe carefully. So now you'll get equilibrium between, let me draw again here, I'll show you what is meant by that. So we have some liquid. Now there is evaporation and there is condensation, right? Both the process occurs and they reach a stage called equilibrium stage. At equilibrium, the molecules present on the vapor phase will exert some pressure on the surface of the liquid. Students observe carefully. At equilibrium, the molecules present on the vapor phase or the vapor above the liquid will exert some pressure on the liquid, on the surface of liquid. That pressure is what we call as vapor pressure. Okay, so what is vapor pressure? Vapor pressure, let me write simply Vp. So what is vapor pressure? Vapor pressure is the pressure, vapor pressure is the pressure exerted by vapor. Vapor pressure is the pressure exerted by vapor above a liquid or solution. Okay, is the pressure exerted by vapor above a liquid or solution at equilibrium. Okay, at equilibrium and at constant temperature and at given temperature. Okay, students, observe this carefully. Here you know what is the meaning for equilibrium. Okay, what equilibrium here? What equilibrium exists here?
Rate of evaporation equals rate of condensation.
Rate of evaporation and rate of condensation become equal. Okay, and this is what we call as equilibrium here. So vapor pressure is the pressure exerted by vapor above a liquid or a solution at equilibrium and at given temperature. Okay, if temperature changes, what will happen? More vapors are formed. If suppose if we increase temperature, you will get more vapor, so vapor pressure will increase. Okay, so whenever you want to define or you want to give a vapor pressure of some liquid, okay, you must mention the temperature, because it is absolutely temperature dependent term. Okay, vapor pressure is temperature dependent term. Now what I'm going to do, so this is what we call as vapor pressure. Okay, now let me take students, observe this carefully. I'll take vapor pressure of liquid solutions. Students, observe carefully. Vapor pressure of liquid solutions. Vapor pressure of liquid solutions. What is meant by that? Listen, suppose okay, before going to see the vapor pressure of liquid solution, I will introduce, okay, a famous law called Raoult's law. R-A-O-U-L-T, Raoult's law. Students, observe this carefully. What is Raoult's law? Raoult's law. Okay, what is Raoult's law? Yeah, the Raoult's law states that suppose a solution contain volatile liquids, okay, then partial pressure, let me write here, according to Raoult's law states that, right, Raoult's law states that the partial vapor pressure, I am using the word partial, why? Because I am taking two liquids. Okay, so that's why I am using the word partial vapor pressure. Assume that both the liquids are volatile liquids. Both are volatile liquids. Okay, so I'm giving the definition like this. Okay, so what is Raoult's law? Raoult's law states that partial vapor pressure of each component of the solution, right, is directly proportional to its mole fraction, right, in solution. Students, observe this carefully. What is Raoult's law? Raoult's law states that partial vapor pressure of each component of the solution is directly proportional to its mole fraction in solution. Okay, this is Raoult's law. Okay, now what's the meaning? Okay, let me explain that with I'll take two liquids. Okay, so assume that I have I'll take a liquid A and another liquid B. I'll take two liquids A and B. Assume that both are sufficiently volatile. They can form vapor readily. Okay. So I have two liquids A and B. Both are volatile liquids. Now first I will take liquid A alone in a container, and students, this I forgot to say few things here. Listen, in vapor pressure, students, observe this carefully. I told you what is vapor pressure. It is the pressure exerted by the vapor above a liquid, okay, at equilibrium and at constant temperature. Okay, that is the definition for vapor pressure. And here you should keep some things in your mind. What is that? I forgot to say that. Let me give that point here. Vapor pressure. Let me write here. Vapor pressure does not depend on. Vapor pressure does not depend on. Okay. Number one. The amount of liquid does not depend on amount of liquid. Whatever amount of liquid you take, okay, and it does not depend on the shape of the container. Students, observe this carefully. Vapor pressure does not depend on amount of liquid. What is meant by that? Suppose I'll take a liquid in a small vessel. I'll take some small amount of liquid. Okay. Assume that if temperature is constant, and I'll take another container which consists of large amount of liquid. Okay, I have large amount of liquid, same liquid, but temperature is same for the two liquid. As long as temperature is same, then vapor pressure of the liquid here, suppose I have a liquid A and this also the same liquid A, the vapor pressure of the liquid A, similarly vapor pressure of the liquid A here, both these pressures should be same. These two are one and the same. What is meant by that? Whether you take small amount of liquid or larger amount of liquid, vapor pressure, okay, is a constant quantity. It does not depend on amount of liquid. Whether you take half liter or 1 liter or 5 liter, that does not matter. If the liquids are same liquids, then at a given temperature, that liquid has some vapor pressure. Okay, vapor pressure is independent of amount of liquid. Keep that in mind. Then second point, vapor pressure does not depend on shape of the container. Okay, the container may be cylindrical like this. Okay, the container may be cylindrical like this, or the container may be like this also, pot like, and it is completely closed. Okay, I am taking same amount of liquid, same amount, right? But if you measure the vapor pressure, suppose I have a liquid A here, and this is also the same liquid A, right? Same liquid and temperature also same. Both are in same temperature. Both the liquids are in same temperature. Then if you measure the pressure of the liquid A in this container or in this container, okay, the pressures are same. I am having same amount of liquid, same amount, same temperature. Only the shape of the container is different. Okay, if you measure the vapor pressures are same. It does not depend on shape of the container. So keep this point in mind. Vapor pressure does not depend on, number one, amount of liquid, number two, shape of the container. Okay, and vapor pressure depends on two things. Number one, as I told you, temperature depends on, number one, temperature of the liquid, right? It depends on temperature, and it also depends on the force of attraction between molecules. force of attraction between molecules in liquid phase. Okay, it depends on force of attraction between molecules in liquid phase. You know very well, if temperature increases, okay, more vapor will go to the vapor phase, therefore vapor pressure will increase, right? Similarly, in the case of so the second factor, that is force of attraction. Students, observe carefully. Suppose I'll take two liquids A and B. Okay, this is liquid A. I'll take another liquid B here. My container is same shape, same size. Okay, I'm taking two liquids A and B, same amount of liquids. Okay, so here 1 liter of A, liquid A. Here also I'm taking 1 liter, but liquid B. Let us assume the attraction between AA molecules. Okay, the attraction between AA molecules, and here the attraction between BB molecules. Suppose if the force of attraction between AA, if it is greater than the force of attraction between BB, okay, what will happen in this case? If molecule-molecule attraction is high, then escaping of this molecule to the vapor phase, okay, is difficult. This is difficult. Why? Because attraction in the liquid phase is high. There's a strong attraction exists between AA molecule. So since in the liquid phase there is a strong attraction, okay, it is very difficult for the molecule to move from liquid phase to vapor phase. So vapor pressure, right? Vapor pressure of A is less compared to vapor pressure of B, because in B the attraction, force of attraction is weak. Therefore more molecules of B will go to the vapor phase. Therefore vapor pressure of B will be more. Students, is this clear? Any doubt? Is it clear, student? Are you able to understand this? Okay, so yeah. See, vapor pressure does not depend on these two things: amount of liquid and shape of the container. Whatever amount of liquid you take, if the liquids are same liquid and if you maintain same temperature, then vapor pressure exerted by the liquid which is present small amount and which is liquid which is present in larger amount are same. Similarly, vapor pressure does not depend on shape of the container. Okay, vapor pressure depends on two things. What are they? Number one, temperature. Number two, force of attraction between molecules in the liquid phase. Suppose I'll take two liquids A and B. Assume that in liquid A the attraction between AA molecules is high. If the force of attraction between AA molecule is high compared to B, okay, in B the force of attraction between BB molecule is less. Listen, if attraction in the liquid phase is high, then tendency for the molecule to escape from liquid phase to vapor phase, to escape from the liquid phase, that tendency decreases. Am I right, student? If there is more attraction exists in the liquid phase, how can the molecule to jump out? How can the molecule escape? So the tendency for the molecule escape from liquid phase to vapor phase, that tendency will decrease. Therefore only few number of molecules will reach the vapor phase. Therefore vapor pressure will be low. Whereas in liquid B, the force of attraction between BB molecule is low. When force of attraction is low, more molecule escape from liquid phase and they occupy the vapor, or they occupy the empty space here. So the amount of vapor become high. Therefore vapor pressure also increase. Is this clear, student?
Yes, sir.
Okay, yeah. Keep this point in mind. I just forgot to say this. This is very important, right? Then now I'll go back to the vapor pressure of liquid solutions. Okay, so I have introduced what is called Raoult's law. What this Raoult's law says that, okay, let me explain that using this idea. So I'll take two liquids A and B. So this is, here I have a container containing liquid A, okay, and evaporation will occur, condensation will occur, then you will get some vapor above the liquid. Okay, you will get some vapor. Let the vapor pressure is PA. PA is the vapor pressure of A in pure liquid A. So I have pure liquid. Okay. Now what I'm going to do, I'll take the same container or similar shaped container with the same volume. I'll take liquid B here. I'll take liquid B. So here also, see, the temperature is same here, right? Temperature is same. At the same temperature, I'm taking liquid B and I'm measuring the vapor pressure of liquid B. Let the vapor pressure be PB. So PA is the vapor pressure of liquid A. PB is the vapor pressure of liquid B. Students, turn on your camera. Hello students, am I audible? Yeah, turn on your camera. Everyone. Hello? Students, am I audible?
Yes, sir.
Right, yeah. So, I have two liquids. So, in liquid A, partial pressure is, liquid A, the pressure is PA. For liquid B, the pressure is PB. Students, observe this carefully. This is pure liquid A. So, I can call this simply as vapor pressure of A. This is pure liquid B. So, this is PB is called vapor pressure of B. Now, what I'm going to do, I'm going to mix these two. I'm going to mix these two in a container. Okay, I'll take a container and I'll mix this A and B. A and B. Okay. Now what I'm going to do, we have formed a solution, okay, which consists of mixture of A and B. In this solution, okay, the vapor consists of both A molecules as well as B molecules. The vapor consists of A molecules as well as B molecules. Okay. Now what is the vapor pressure exerted by A molecules alone on the solution? We call this pressure as students, and there is a notation we have to follow. In the case of pure liquid, we should put a naught symbol at the superscript. P naught A means it is the vapor pressure of pure liquid A. P naught B means it is the vapor pressure of pure liquid B. Okay. Now we have come to solution. For solution, we have to apply Raoult's law. Okay. What's Raoult's law says that now I have a mixture in the vapor. I have a mixture of A and B. In this mixture, what is the pressure exerted by A alone? We call it as partial pressure of A. Partial vapor pressure. Partial vapor pressure of liquid A. Partial vapor pressure. Why I am calling partial vapor pressure? Because it is not pure now. I have a mixture. Whenever you have a mixture of gases, then pressure exerted by each gas should be called as partial vapor pressures. So what is the partial vapor pressure of A here? Partial vapor pressure of A, which is nothing but PA. According to Raoult's law, partial vapor pressure of each component A and B is directly proportional to its mole fraction in solution. Okay, so partial pressure of A in the vapor phase is directly proportional to the mole fraction of A in the solution. Okay, in solution we have some mole fraction of A and we have some mole fraction of B. Okay, what is the mole fraction of A? You see, or you calculate, then the partial pressure should be directly proportional to mole fraction of A present in the solution. This is called Raoult's law, right? At a given temperature. Okay, it says that partial vapor pressure of each component of the solution is directly proportional to its mole fraction in solution at a given temperature or at a constant temperature. We have to include this term. Temperature should be constant. Okay, and this is what we call as mathematical form of Raoult's law. Students, is this clear? Any doubt? Students, turn on your camera.
No doubts.
Everyone, turn on your camera. Okay, similarly, I can write partial vapor pressure of the component B is directly proportional to mole fraction of component B present in the solution. This is what we call as Raoult's law. Okay, Raoult's law is applicable for solutions, not for pure liquids. Okay, we won't apply Raoult's law for pure liquid. We'll apply Raoult's law for solutions. Okay, so here I have taken liquid solution. Okay, liquid means both A and B are liquids. Both solute and solvent, both are liquids, and they form a solution. Okay, in that solution, partial pressure of A is directly proportional to mole fraction of A, and partial pressure of B is directly proportional to mole fraction of B. Okay, now we'll see some more information here, which is very important. Students, observe carefully. So I'm discussing about liquid solution. Okay, now we have a container, and this container consists of a solution containing mixture of liquid A and liquid B. We have a solution containing two liquids A and B. Okay, and above the liquid surface we have vapors, and the vapor consists of both A molecules and B molecules. So in the vapor we have A molecules as well as B molecules. Both the molecules will be there. Okay, and according to Raoult's law, we can write the partial pressure of A, okay, in solution, partial pressure of A in solution is directly proportional to mole fraction of A present in the liquid phase. Okay, or if I equate this, we should introduce a constant. That constant is nothing but P naught A. That constant is nothing but P naught A. Students, can you tell me what is this P naught A? What is PA? What is P naught A?
Partial pressure of saying
Yeah, this is partial pressure of liquid A in solution. This is vapor pressure. This is partial vapor pressure. Okay, let me write here. What is PA? PA is nothing but partial vapor pressure of liquid A or A, component A in solution. Whereas P naught A, it is not partial, it is pure. Okay, so P naught A is the vapor pressure. So vapor pressure of pure liquid A. Okay, it's the vapor pressure of pure liquid A. It is not a solution. Okay, so this is the what is called the Raoult's law. Right. Similarly, we can also write for the component B, partial pressure of component B, right, in the vapor phase, it is directly proportional to mole fraction of component B present in the solution. Right. Or if I equate this, I should introduce a constant called P naught B into XB, where PB is vapor pressure or partial vapor pressure of component B in solution. This is vapor pressure of pure B, pure liquid B. Okay. Now students, observe this carefully. This equation, it is something similar to y is equal to mx, correct? It appears like a straight line, but intercept is 0. That means the straight line should pass through origin. So if I plot partial vapor pressure of A, okay, partial vapor pressure of A in a solution, right, in y-axis, and mole fraction of A, mole fraction of A in the liquid phase, if I plot, we will get a straight line passing through origin. Mole fraction, as mole fraction of A increases, vapor pressure also increases. Vapor pressure also increases, right, at a particular temperature T. Okay. Now the slope of this straight line, what is the slope? The slope is equal to P naught A. Slope is equal to P naught A. So if you want to know what is the vapor pressure of the pure liquid A, okay, just plot a graph between PA and XA. You will get a straight line. Okay, find the slope of the straight line. The slope of the straight line will give you vapor pressure of the pure liquid A. Is this clear, student? Similar graph you can plot for B also. Students, is this clear? Any doubt? If you find any difficulty, you tell me.
No, sir.
This is,
No, sir.
yeah, this is according to Raoult's law. This is according to Raoult's law. According to Raoult's law, partial vapor pressure of a component A is directly proportional to mole fraction of that component in solution. Okay, this is according to Raoult's law. According to Raoult's law, we can write partial pressure of A like this and partial pressure of B like this. Okay, now let me go to the, let me extend this further. So we have solution. I am taking the same solution consisting of the liquids A and B, okay, and the vapor above the liquid also contain A and B. The vapor above the liquids, I have vapor here, that vapor above the liquid also contain A and B. Okay, now what I am going to do, for the vapor phase, I am going to apply a law called Dalton's law. Dalton's law. What is Dalton's law? What does this law says? According to Dalton's law, students, observe carefully. According to Dalton's law, see in the vapor phase I have two component A and B. Okay, you measure the total vapor pressure PT. What is PT? PT is the total pressure. Total pressure means it is the pressure exerted by both component A and B. Okay, this are experimental pressure, we can say the other way, total pressure. According to Dalton's law, partial pressure of A in the vapor phase, partial pressure of A is directly proportional to, students, observe carefully. According to Dalton's law, the partial pressure of A is directly proportional to mole fraction of A present in the vapor phase. I repeat, what is YA and YB? YA is the mole fraction of A present in the vapor phase, and YB is the mole fraction of the component B in the vapor phase. Right? So in Dalton's law, we are relating partial pressure of component A with the mole fraction of component A in vapor phase. Whereas in Raoult's law, see the difference. In Raoult's law, we have related partial pressure of A with the mole fraction of A in solution. See the difference. Okay, here XA is the mole fraction of A in solution, whereas here I am using the term YA. YA is the mole fraction of A in the vapor phase, because in the vapor also I have a mixture of A and B. Okay, so according to Dalton's law, partial pressure of A is directly proportional to mole fraction of A present in the vapor phase. Or I can also write this as PA equal to, right, equal to total pressure PT into mole fraction of A. This is what we call as Dalton's law. Total vapor pressure. Right? Similarly for the component B, partial vapor pressure of component B is directly proportional to mole fraction of component B present in the vapor phase. And I can say that PB equal to YB into X into total pressure. Into total pressure. Okay? Students, is this clear? Any doubt? Are you comfortable with this? Students, is this clear?
Yes, sir.
Yeah.
Yes, sir.
Yeah. Now what I'm going to do, so this is Dalton's law. I'll come back to the Dalton's law later. Okay, just keep this in mind. Now I'll go to the Raoult's law. Okay, let me define the total pressure. Okay, theoretically, I'm saying theoretically. So theoretical total pressure. Theoretically, what is total pressure? Total pressure is nothing but partial vapor pressure of A, component A, plus partial vapor pressure of component B. Am I right? Because in the vapor phase we have only A and B. So if you know what is the partial vapor pressure of A and partial vapor pressure of B, yes, you can say the total pressure. So theoretically, total pressure is nothing but equal to partial pressure of A plus partial pressure of B. Okay, according to Raoult's law, what is partial pressure of A according to Raoult's law, students? According to Raoult's law, yeah, according to Raoult's law, it is P naught A into mole fraction of A in, what is this?
The solution.
Mole fraction of A in solution. Okay, plus what is PB? PB is vapor pressure of pure B into mole fraction of B in solution. Correct? So this is called the total vapor pressure. Total pressure, right? So total pressure equal to this. Okay, and you also know, since we have taken binary solution, in binary solution mole fraction of A plus mole fraction of B should be equal to 1. Therefore I can write this mole fraction of A as, I'll keep this P naught A as such. I can write this mole fraction of A as 1 minus mole fraction of B plus P naught B into XB. Is this correct, students? Just check it. Is this correct?
Yes, sir.
Okay, because XA plus XB is 1, therefore XA should be equal to 1 minus XB. So I replaced this XA by 1 minus XB. Now we can make some more simplification here. Okay, let me write the next page. So what I'm going to do, I'll multiply with the P naught A. So you'll get P naught A minus XB into P naught A plus P naught B into XB. Okay, now I can take PB as XB as common, so I can write this as P naught A. I'll keep P naught A as such, plus here I'm going to take XB as common. I'll take XB as common. Now let me write positive term first, that is P naught B, and the negative term next, P naught A. So this is my total pressure. Okay, it is actually the theoretical total pressure. Students, observe carefully. Calculated, okay, theoretical total pressure. So what is the theoretical total pressure? Theoretical total pressure is nothing but vapor pressure of pure A plus vapor pressure, the difference between the vapor pressures of pure B minus pure A, the difference, and multiply by vapor pressure of A. I'm sorry, mole fraction of A. Okay. Is this clear, students? Any doubt here? Any doubt?
No, sir.
Okay, yeah, take down. Take down. This is very, very important. This is applicable for all liquid solutions. Whatever liquid solution you take. Okay, if you want to calculate theoretically what is the total pressure, you can use this formula. It is purely theoretical formula. Right? But to calculate total pressure, you require pure vapor pressure of pure A, vapor pressure of pure B, and the mole fraction of B in the liquid phase. Either mole fraction of B or mole fraction of A. Because if you know what is the mole fraction of A, you can find the mole fraction of B. Now, what I'm going to do, I'm going to plot all these values. Right? Yeah. Students, observe this carefully. So we have taken a liquid solution. Okay. In liquid solution, this is the equations we derived. Right? So we had seen three equations based on Raoult's law. What are the three equations? Vapor pressure, partial vapor pressure of A is equal to vapor pressure of pure A into mole fraction of A. Okay. And partial vapor pressure of component B is equal to vapor pressure of pure B into mole fraction of B. I can also write this in terms of B. How? I'll keep this P naught A as such. I'll replace this XA as 1 minus XB. So that vapor pressure is related with the mole fraction of B. Vapor pressure is related with the mole fraction of B alone. Okay. Similarly, we had seen that theoretical total vapor pressure is equal to P naught A plus P naught B minus P naught A into XB. So we have three equations. All these equations, okay, they appear like straight line equations. They are all equations of straight line. So what I'm going to do, I'm going to plot these, right? And I'm going to show you how these look like. So I'm going to plot vapor pressure in y-axis and mole fraction of B, right, in x-axis. Here mole fraction of B is 0, here mole fraction of B is 1. You know very well, if it is pure liquid B, then mole fraction should be 1. Okay, mole fraction should be 1. If it is pure liquid A, then mole fraction should be 0. Okay, now students, observe carefully. If XB is 0 here, XB is 0 means, students, observe, XB is 0 meaning we have pure liquid A. Pure liquid A, only we have pure A. If mole fraction of B is 1, which means we have pure liquid B. That's the meaning. So here mole fraction of B is 0, that means I have only pure liquid A. So for pure liquid A, we have some vapor pressure, let it be P naught A. When the mole fraction of B is 0, which means we have only pure liquid A. So for pure liquid A, the vapor pressure is P naught A. Similarly, at XB equal to 1, when XB is 1, we have pure liquid B. For pure liquid B, we have some vapor pressure. Let us assume the vapor pressure of pure B is somewhat high compared to A. I'm sorry, this is B. Okay, B vapor pressure is high compared to A. Just assume like this. I have a solution like that. Now what I'm going to do, what happens as xb increases from 0 to 1. Here as xb increases, students listen carefully, as xb increases we are taking 1 minus xb, therefore vapor pressure of A decreases. So vapor pressure of A decreases right along this line. I'm just showing this is vapor pressure of A, or partial vapor pressure of A. Partial vapor pressure of A decreases as the mole fraction increases. Why? Because if mole fraction increases, we are taking 1 minus xb, so 1 minus xb will decrease. xb increases, but 1 minus xb will decrease. Therefore partial pressure or partial vapor pressure of A decreases. Similarly, what about partial pressure of B? Partial pressure of B, as xb increases, right, when we move from left to right, mole fraction of B increases. If mole fraction of B increases, vapor pressure of B also increases. Vapor pressure will increase. Okay, what about the total vapor pressure? Theoretical total vapor pressure. As xb increases, okay, you see these two. Students listen, in this case I have taken, right, I have taken P naught B is greater than P naught A. P naught B minus P naught A. See, P naught B value is high, P naught A value is low. Therefore P naught B minus P naught A is a positive one. So this is a positive quantity in this case. In this case, I am assuming like that. If this is positive, this should be positive. In this case, if mole fraction of B increases, total pressure also increases. Yes, total pressure increases. So this line indicates total pressure. Okay, students, turn on your camera, all of you. Students, am I audible? Turn on your camera.
Yes, sir.
Right? So this is what we observe. This is what we observe when we plot PA, PB and total pressure. For PA and PB I have shown those straight line with the dotted lines. Okay, I'm showing the total pressure in a thick line or a solid line. Okay, we'll get straight lines. I'll tell you why we get straight line when you plot all these things. Is the graph is same for a real liquid? I have told you it's a theoretical, right? It's a theoretical total pressure. If you take the actual experimental total pressure, do we get the same type of graph? When we'll get the same type of graph, that depends upon what type of liquid mixture you are taking. Okay, so what I'm going to do in the next class is that I'm going to discuss two things. What is that? Suppose if you take a solution containing mixture of two liquids, say liquid A and liquid B, mixture of two liquids. In this case, there are two possibilities. Students, observe carefully. There are two possibilities. What is meant by that? If the experimental total pressure, okay, let me take this as experimental or observed. I'll put OBS, observed, or also called experimental. If the experimental total pressure, if it is exactly same or roughly same, equal to the theoretical total pressure, theoretical total pressure, that is calculated. Okay, we have calculated, no? See, using this formula, Raoult's law, using Raoult's law we have calculated total pressure, right? This is called theoretical total pressure. If the experimental total pressure and the theoretical total pressure, if these two are equal or roughly equal, okay, for most case it may not be 100% same, but roughly equal. If they are roughly equal, we call those solutions as ideal solutions. Ideal solutions. Okay, suppose if the observed pressure or the experimental pressure total pressure, right? Observed total pressure and theoretical total pressure, theoretical, right? If they are not equal, if suppose they are not equal, we call those solutions as non-ideal solutions. Non-ideal solutions. So this is what we are going to discuss in the next class. What is meant by ideal solution? What is meant by non-ideal solution? If the solution is ideal solution, I will get exactly same type of graph. I will get straight lines. For PA, for PB, this is PB. For PA, I got straight line. For PB, I got straight line. And for total pressure also, I got straight line. We'll get straight line. We'll get straight line if the solution is ideal solution. What is meant by ideal solution, students? What is meant by ideal solution? When we can call a solution is ideal?
And the observed P total equals theoretical P total.
Okay. If the observed total pressure and theoretical total pressure, if these two are equal, we call the solution as ideal solution. If they are not equal, we call the solution as non-ideal solution. Is this clear, students? Okay.
Yes, sir.
Yeah. Right. I stop here. We'll continue this in the next class. Right.
Thank you, sir.
Thank you, sir.